At the beginning of the semester, I have my linear algebra students take a quick 9-question preference survey. Are they a morning glory or a night owl? Do they prefer summer or winter? Camping or a resort? Questions like that. These questions do more than tell me about their personalities, though. With a new way to analyze the data, this simple survey can actually predict their test scores. Even though I have 9 questions from the survey, some of the responses are related to other responses. For example, students that prefer camping to resorts probably prefer summer over winter. So the response of a student on one of these might help me predict what their response would be on the other one. The reason for this is that there might be an underlying variable or underlying variables that are driving their responses in some of these questions, and these same underlying variables might contribute to how they perform on tests. In this video, we will analyze this data and show that the mathematical problem we are trying to solve is a problem that comes up in a lot of different situations. And what we will develop is perhaps the most powerful idea in all of linear algebra: eigenvectors and eigenvalues. Before we dive in, I need to do a quick review of bases and of change of basis. In a previous video, we shared several examples to show how helpful or needful it is to change a basis. We can think of a basis as the coordinate axes, or a set of units we use to describe points and vectors in a given space. One example is changing between color models. Your screen uses values of red, blue, and green to know the color to light up each pixel. However, a color printer uses cyan, magenta, and yellow, so converting between RGB and CMY is a change of basis. We can accomplish this change through matrix multiplication. This way, we can describe the same color in either color model, but the values will be different. Another example we explored in the previous video that connects directly to our preference survey problem was shirt size based on body measurement. I found a dataset with a bunch of body measurements for adult males. We plotted neck, chest, and abdomen circumference, and these values are all pretty correlated. We explained that for a clothing manufacturer, it makes a lot of sense not to use these 3 sizes for a shirt, but only 1 size. And the way they decide what each size shirt should be is to find this dimension. The longest dimension through the data would be the values of shirt sizes that would best fit adult males, while the secondary dimension, orthogonal to the first, represents body shape. For example, a fit shape with less abdomen and more chest versus a body with less chest and more abdomen. This helps clothing manufacturers know how to make variations in shirts of the same size to help fit more bodies. But here's the mathematical question we need to explore. How do we find those primary and secondary dimensions given the data? If we only have 2 or 3 variables, we can just pick points to get a good approximate line that runs through the long axis of the data cloud. In our preference survey data, we actually have 9 dimensions. That's too many to plot and analyze graphically. But I really want to know the primary dimension of the data cloud because it usually says something very important about the underlying variables captured by the responses. So how do I find the primary and secondary dimensions without the ability to graph the data? Well, it seems the primary dimension is related to the correlation of the variables. The reason we have this long primary dimension in the body measurement example is because as one of these measurements increases, the other 2 tend to increase as well. That is the idea of positive correlation. Very high correlations are tightly clustered around a line. So how does this help us? Well, look at the patterns we see as the level of correlation changes. From a 0 correlation where the data cloud is circular to more ellipse-shaped to a line. These remind me of a GeoGebra app we used in a previous video. We use this to explore matrix transformations. The circular face ends up as an approximate ellipse with many transformations and can even be compressed to a line. So how are these transformations connected to correlations? Well, we can try some correlation matrices to see what transformation they create. A correlation matrix is a matrix that shows the correlation of each variable in a dataset with all other variables. In a correlation matrix, the diagonal entries will always be 1, because that's a perfect positive correlation, which always happens with the correlation of a variable to itself. Here's the correlation matrix for the neck, chest, and abdomen variables. Here's the correlation matrix of the 9 preference survey responses. With only 2 variables, the matrix has 1s down the diagonal and the correlation of the 2 variables in the off diagonal. If we keep the off diagonals as 0, we just have the identity matrix, so there is no change in the transformation. The circular face stays circular. but as the correlation moves to 1 or to a -1, we see the ellipse shape emerge and then condense to a line. The problem we're trying to solve is to find the primary axis of this ellipse. That is this dimension if the correlation is positive, or this dimension if it is negative. If we play around enough, we can start to see something special about this dimension. It looks like this transformation stretches along one of these dimensions and compresses along the other. Look at what happens to these vectors. When these are transformed, they're stretched or shrunk, but they stay on the same line or their own span. That is different than vectors that are not on one of those lines. So finding the primary dimension of correlated data is really trying to find the vectors that are simply scaled by the correlation matrix. This is huge. Mathematically, this allows us to set up an equation where we can solve for these dimensions, which we will do momentarily. The vectors that are scaled by a matrix multiplication have a special name, and the scale factor of that matrix transformation also has a special name. The reason they have special names is because vectors that are scaled by a matrix are so important in analyzing the matrix. Some might say they are the most important thing to know about a matrix. We will share many applications of these special vectors and values at the end of the video. The special vectors that are scaled by the matrix multiplication are called the eigenvectors, and the scale factors of that scaling are called the eigenvalues of the matrix. Eigen is a German prefix that means self or proper or characteristic, as in a fundamental characteristic of a matrix. So in English we might call them fundamental vectors and fundamental values, or master vectors and master values to a matrix. So how do we find the eigenvectors and eigenvalues of a matrix? The process takes several steps. We will walk through the process for a simple 2x2 correlation matrix by hand, then use a computer to help us with the survey data. The process of finding these by hand matches what's taught in typical linear algebra classes. If you're in a class where you need to do this process by hand, then I strongly encourage you to study this process so you understand the logic of each step in this long process. If you're not in a linear algebra class, the process still can be insightful. Let's start by calling the correlation matrix A, and the scaling factor of the vector in the primary dimension, S. Then we want to find vectors x bar so that A times x bar equals S times x bar. We will work through this equation with the general form as well as a specific example with just the neck and abdomen data, which has a correlation of about 0.75. For example, we can try to subtract the right side from the left side and factor out x bar. But here's our first problem. We end up with a matrix minus a scalar, and that operation is not defined. We can modify this x times x bar term into an equal expression with a matrix multiplication using the identity matrix. We can rewrite it as s times I times x bar. So we can factor out the x bar because we have a matrix minus a matrix of the same size, as long as we pick up the identity matrix that's the same size as the correlation matrix. This is the equation we have to solve to find the eigenvalues and eigenvectors. The matrix has s subtracted off the diagonal, and we can now have a matrix times x bar that must equal the 0 vector. We know from previous videos that this will happen in two cases. One, if x bar is 0, which is a case that isn't very helpful in solving real-world problems, because we want to know non-zero vectors that get scaled. Or the matrix A minus Si is non-invertible. We can find out when A minus Si is non-invertible by finding what values of S make the determinant of that matrix 0. Calculating the determinant, setting equal to 0, and solving for S requires solving a polynomial equation, which we can sometimes do by factoring, but we usually do in practice with the help of computers. We find two answers for S in our case, 7/4 and 1/4. These are our eigenvalues. Now we can plug each of these back into our equation to make two equations. We can interpret these equations as trying to find the vectors x bar that become 0 when multiplied by a matrix. These are really two systems of equations with infinite solutions, and we can solve these accordingly through row reduction or through using a computer. Technically, the solution of a system where the right side is the 0 vector is called the null space of a matrix. So you can think of this step as finding the null space of each of these matrices with the eigenvalues subtracted off the diagonal. If you had a linear algebra class, you would have been taught how to find the basis for a null space. We find that any scaled version of the vector 1, 1 or a -1, 1 are the special vectors we're looking for or in other words, these are the eigenvectors of the correlation matrix. Yes, technically there's a whole family of vectors, because any scaled version of these vectors is still scaled by the correlation matrix. We can check to make sure that these vectors are scaled by multiplying each one by the correlation matrix. And indeed, we get 7/4 times the first and 1/4 times the second. Now, that was a lot of work, but it is very important work. In applied problems outside of a classroom setting, we can have a computer find the eigenvalues and eigenvectors for us. Wolframalpha.com is a website that will automatically find the eigenvalues and eigenvectors of a square matrix just by entering in that matrix in the search bar. So which of these vectors represents the primary direction and which one represents the secondary direction? Well, the eigenvalues can tell us that. Since the eigenvalues tell us the scale factor of each dimension, the larger scale factor will stretch in the primary dimension and the smaller one, which happens to be smaller than 1 in this case, shrinks in the direction of the second dimension. Now that we've done the mathematics, we can go about solving our real-world problem, analyzing the preference survey for my students. I will create the correlation matrix and have an online calculator find the eigenvalues and eigenvectors for us. The eigenvector associated with the largest eigenvalue will be the primary dimension through the dataset. The largest eigenvalue in our case is 1.67, and the primary direction that data stretches is in this direction, the eigenvector associated with the largest eigenvalue. For this analysis, the vectors with higher eigenvalues are more important dimensions than those with lower ones. We will just look at the first one today. The largest numbers tell us the variables that are most important for this vector. And one rule of thumb for analyzing these vectors is to scale them to a length of 1 and look at the variables that are 0.4 or larger in absolute value. These 4 questions on the survey that are most important for this first vector are these 4. Preferring one of the items on the left means you are more likely to prefer others on the left. Similarly to the right. These individual survey items are probably capturing a more fundamental trait from the students. What would you say we're measuring with these 4 questions? Someone pointed out that these might match to the type A and type B personality traits. Type A tends to be organized, well-prepared, and tends to have higher stress, while type B tends to be more go with the flow, easygoing, resulting in less stress. Whatever we call this dimension, I was wondering if a variable that scored students on this scale would be associated at all to their learning. So I ran a quick regression with this type A, type B variable against students' first midterm scores. About 80% of the students put their real name on the survey and allowed me to match up their scores. The variable was a significant predictor of midterm scores, with those more at the type A end tending to score higher, and the type Bs scoring lower. But it was not a strong predictor with an R-squared around 0.04, so don't freak out if you're a type B student. You can still do well in the class by studying hard. Okay, so what did we learn? We found that important dimensions of multivariable data are the directions represented by a vector that is scaled by the correlation matrix, and technically the covariation matrix as well. The directions that are stretched or shrunk are called the eigenvectors of the correlation matrix, and the amount the vectors are scaled are called the eigenvalues. And just for future reference, finding the important dimensions of data this way is called principal component analysis. We went through the logic of the long process on how to calculate the eigenvectors and eigenvalues. It is an important process to be able to do by hand in many linear algebra classes, but the logic of the process is important to understand even if you use a computer to calculate the eigenvalues and eigenvectors. What is amazing is that eigenvalues and eigenvectors open up an entirely new way to analyze phenomenon and are critical in so many applied fields and problems. We won't take time to list all of them, but here are a bunch that ChatGPT generated. We hope to explore the power of eigenvalues and eigenvectors to solve real-world problems more in later videos. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.